All right, let's look at period dependency for pendulums and mass spring oscillators. Now, both of these are examples of what we call simple harmonic motion. You've seen this term come up. I don't think we've defined it. Simple harmonic motion occurs when you have a restoring force that's driving a system back to equilibrium. So with the pendulum, that was the force of gravity, the component tangential, and with the spring force, or with an oscillator, that's spring force. You stretch it this way, spring force is pushing back. You stretch it up, spring force is pushing down. Now you do have gravity factored in as well, but those are the driving forces causing repeatable motion. And as long as we don't have other external forces, this will repeat itself in perpetuity. Now, what is the period dependence? Now, we just went over this where we derived an equation from our data, and many of your equations that you came up with looked something like this. The period is equal to some number approximately 2 times the length to the 1/2 power, which is true, which is a power function with a square root function here. L to the 1/2 is square root of L. And so what we see, it's not dependent on mass. It's not dependent upon how far you bring it back, the angle theta, but it is dependent upon the length of the string. Now this 2 really is 2 pi times 1 over the square root of g, where 2 pi is a little more than 6, square root of g is a little more than 3, since that's 9.8. And so our official formula, the period of a pendulum, will be 2 pi times the square root of L over G. And you see L as L or capital L sometimes, little l or capital L. So this is what my period depends on for a pendulum. Now you see this is on the equation sheet. But sometimes it's useful to write this in terms of the frequency. So since we know that frequency is the inverse of the period, then the frequency of a pendulum will be the inverse 1 over 2 pi times the inverse of this. So I flip G and L. So as L increases, T increases, and as T increases, the frequency goes down. So these are inverses of one another. So there is your pendulum. Now, this mass spring oscillator is similar. When we allow this to oscillate back and forth, right, there's always a net force restoring it back towards equilibrium. And we see that this period is dependent on mass, which is different from the pendulum. When we increase the mass, there's more inertia here, and as the spring system oscillates back and forth, right, this will tend to slow the oscillation. Therefore, as period goes up, mass goes up. Or as mass goes up, period goes up. I should probably flip these, right? The direct relationship there. Well, what else impacts it? Well, it turns out that amplitude does not significantly impact it, so long as you don't exceed the elastic limit. And one of the reasons for that is, as you stretch it more, the forces cause greater accelerations. If you stretch it only a little bit, there's less of an acceleration. And that ends up canceling out in the derivation. So amplitude does not affect period. But what else does is the stiffness of the spring, which we call our K value. So a really stiff spring will start oscillating back and forth really quickly, because the forces will be stronger. Since force depends on displacement, a little bit of displacement creates a bigger force, which creates a bigger acceleration, therefore a shorter period. So when K increases, period decreases. Okay? So we have mass direct, K indirect. And it turns out this formula takes on a very similar look. T for a mass spring oscillator is equal to 2 pi times the square root. Now we saw there's a more direct relationship here, so M and an inverse relationship here over K. So it depends on the mass on the spring and the tens of the K of the spring. Now, just as we did with the pendulum, we can rework this to write it in terms of frequency. So the frequency will be 1 over 2 pi square root of K over M. This is another given equation on your AP1 equation sheet for the period of a mass spring oscillator. And notice the similarity between the period of a pendulum. Both examples, oh shoot, I just realized I'm way off the screen for this. I haven't been looking at my screen. So here, I'll go back for a sec. So hopefully you were able to pick that up as I was speaking. And there are your equations for period of a pendulum and mass spring oscillator.